low-cost controller IC for SynJet LED cooler.
All right, good afternoon, ladies and gentlemen. My name is Garrett Larson. This is Mohammed Zaman, John Clark, and Mohammed Zia. We're all WE majors, and together we formed the team that worked on the YouTube design project, sponsored by Texas Instruments and SynJet and Nuventix. Now, to give you a little background, Nuventix develops a unique line of LED coolers for the emerging LED cooling market. Specifically, our project deals with the high-volume light bulb market. We're trying to achieve a very low-cost device for Nuventix. Now, Texas Instruments produced one of the original controller ICs for Nuventix's technology, a product known as C1000. Now, while the C1000 provides sophisticated control, it is overly expensive for the high-volume market where individuals sense mass. We would like to see approximately a 70% reduction for Texas Instruments devices so that they can achieve a better profit margin for Nuventix. Now, our first design problem is what measurement we want to grab. From the motor, we can achieve the voltage across, the current, and the backwards EMF. Of those metrics, for our low-cost system, we decided the back EMF, backwards EMF, is the best metric to look at. And the reason is because the backwards EMF is from the law of generators, voltage generated across the motor by the velocity of it. So if we know the back EMF at a given time, we know the rough velocity of the motor, and we can drive the displacement. So that forms the basis of the metric we're looking at for our control loop. Now, from there, how do you actually physically grab the backwards EMF? We opted for the implementation of the sense coil, and we'll be speaking with Nuventix over the summer about actually physically implementing a prototype sense coil in the motor. And all a sense coil is a single-stranded coil placed in parallel with the motor, and it allows you to see at any given time the backwards EMF in the motor will be reflected as a scaled fraction into that sense coil. We take that scaled sense coil, compare it against vacuum target, and the basis of the control loop. And that brings us to the next part, is the actual setting of the control loop. Over the course of the semester, we looked at a variety of topologies, motor controls. I myself looked at a PID solution. Zaman and John both looked at sigma delta, and we looked at resonance tracking through a perspective of potential phase lock loop, which Mohammed Zia also worked on. Ultimately, however, we discarded almost all of those. We went for a custom IC solution that involves only 3 op-amps for the basis of our controllers. The first op-amp generates a sine wave. It needs a sine wave to operate. The second one is our driver and variable gain stage, and that's achieved with a transistor in feedback.